Hello students. So in the last lecture, we were discussing about the Fraunhofer diffraction due to single slit. We already discussed what is Fraunhofer diffraction and how it is a limiting case of the Fresnel diffraction. Right. In the last lecture, we finished our discussion on this, finding out this amplitude of all the superimposing waves or the superimposing secondary wavelet source at any instant or at any point. Right. So this is the amplitude we got in the last class. This is from the elementary discussion we did. So A is equal to A naught sine alpha by alpha. Then intensity at any point depends on alpha, and alpha is already, we know that alpha 2 alpha is the phase difference between first secondary wavelet source and the last secondary wavelet source, and this is equal to 2 pi by lambda into part difference between them. The part difference between the first secondary wavelet source and the last secondary wavelet source is a sine theta. So 2 alpha is equal to 2 pi by lambda a sine theta, and our alpha is pi a sine theta by lambda. Okay. So this eventually the intensity or the amplitude of the superimposition of all these secondary wavelet source depends on theta. If alpha depends on theta, then the I depends on theta as well, right? So this is the intensity distribution, and the intensity distribution will depend on theta. But first we need to find out what is the central maxima. Now if you look at this, the intensity distribution, now this is our central maxima and these are our secondary maxima. Why this is central maxima? I already told you the central maxima because this is at the center point, and this maxima is because of the undiaphracted rays, not the diffracted rays. These are actually because of the undiaphracted rays, right? So if I find out this, try to find out this, what is the intensity of the central maxima, then I need to put the angle between angle of the diffraction, and the angle of diffraction theta is 0 in this case, right? Because the rays which are falling on this are not diffracted. So if these rays are not diffracted, then theta angle is 0. If theta angle is 0, then obviously alpha is angle is 0, because alpha is directly proportional to, because alpha depends on theta. Okay, alpha depends on theta. If theta is 0, alpha is 0, then I intensity is equal to what? Then now we got this term, that I is equal to a square, which is actually equal to a naught square sine square alpha by alpha square. Now put alpha is equal to 0. If you put alpha is equal to 0, then my intensity comes out to be a naught square sine square 0 is 0 upon 0. Now this is undeterministic form. We cannot find it out. Not determined. Then how do I find out this? So to find out this, I need to use L'Hopital rule. Why? Because my theta is tending towards 0 and my alpha is tending towards 0 as well. Then if I use the limit alpha is tending towards 0 according to L'Hopital rule, then a naught square sine square for amplitude a is equal to a naught sine alpha upon alpha. Now apply the L'Hopital rule, d by d theta alpha, differentiate it with respect to both the numerator and denominator with respect to the variable alpha, and you will get that this is d alpha by d alpha is 1, and this is actually limit alpha tending towards 0, this is cos alpha, which is actually equal to 1. So my amplitude is only depending on a is depending on a naught. A is equal to a naught. That implies intensity for the central maxima is a naught square. So intensity comes out to be a naught square. So this is my intensity, and that's what I used over here, that I is equal to I naught, and I naught is equal to n square r square, which is a naught square. Okay, now let's find out and let's prove the condition for minima. Then how we got this condition, that whenever delta, the part difference, is equal to a sine theta is equal to n lambda, we have our minima position over there, and whenever this is equal to this much, we have our maxima position over there. to find out the minimum position, let's find out the minimum position. Whenever our amplitude is 0 at any point on the distribution, at any point on the distribution, whenever our point satisfy amplitude 0 or intensity is 0 at any point over there, then that point is a point of minima, right? So to find out that, I will put my amplitude as a sine alpha by alpha. I will put my amplitude as 0 or tending towards 0. So for minima, now this is our amplitude. Whenever a is 0, that implies sine alpha is 0, that implies alpha satisfies plus minus n pi. So alpha can be 0 at 0 plus minus whenever n is equal to 0, plus minus 1, plus minus 2, and so on, plus minus 3, and so on. Okay, but n cannot be 0. Why n cannot be 0? Because when n is equal to 0, alpha is permanently 0, and alpha is 0 at that case, we are getting central maxima. So n at n is equal to 0, we don't have any minima, we have the central maxima over there, because this satisfies the condition of central maxima. So alpha is equal to plus minus n pi satisfy the minima positions, but n cannot be 0 for that position, for that condition. Okay, so n starts from plus minus 1, 2, plus minus 2, plus minus 3, and so on. So put this value, put the value of alpha. So alpha is equal to this. Now already we know that alpha is equal to pi by lambda a sine theta n, because 2 alpha is equal to this much, then 2 cancel out, and alpha is equal to this much, and this is equal to n pi. Pi to pi cancel out, and we got that a sine theta n is equal to n lambda. Whenever this condition satisfies, we get the minima position on our pattern intensity spectra. Okay, now the next thing is, we got this condition. Now we need to find out the maxima positions. Now for maxima, for the central maxima, we already got the central maxima condition. Now we need to find out the secondary maximas. For the secondary maxima, now this is an alternative form of the minima. Then whenever our alpha satisfy this 2n plus 1 pi by 2, because whenever alpha satisfy the n pi, means the opposite phase, then we got the minima. But whenever 2n plus 1 pi by 2 set condition is satisfied by alpha, then we got the maxima. So whenever alpha is equal to 3 pi by 2, 5 pi by 2, 7 pi by 2, we got our secondary maxima. And when alpha is 0, we got the central maxima. When alpha is equal to 3 pi by 2, 5 pi by 2, 7 pi by 2, we get the minima positions. Okay, so for first secondary we get the maxima positions. For first secondary maxima, put alpha is equal to 3 pi by 2, then intensity, in the intensity relation, I is equal to I naught into sine alpha by alpha square. So when we put alpha is equal to 3 pi by 2, put this value, we will get a constant term. Then I naught I already know, then I naught upon this into this, then this comes out I naught by 22. So this is already a reduced value, or a less value than I naught, because this is divided by 22 times. So this is already very less, very less than I naught. So that's why intensity decreases in Fraunhofer diffraction. Now this intensity is less than this intensity central maxima. Then next intensity will be lesser than this one as well. Then the next intensity will be lesser than these all as well, and so on, so on, so on. So intensity is for first secondary maxima, the intensity is I naught by 22. For second secondary maxima, put the alpha is equal to 5 pi by 2, and we get that I is equal to I naught by 61. Now this is all very less than this as well. Means secondary maxima have decreasing intensity. All the maximas are of decreasing intensity. Then find the direction of these secondary maxima. If we find the direction, means at what point. Now if this is my point from where the slit, then at what angle this is coming out, at what angle this is coming out, at what angle this is coming out. This is very easy. Put the value of alpha into theta, so you will get already that. But to mathematically, if I evaluate, this is our intensity relation For maxima and minima condition, di by del alpha should be equal to 0. For maxima, the double derivative should be negative as well. So del I by del alpha is equal to 0. When I differentiate del I with respect to alpha, I get this condition tan alpha is equal to alpha. So this condition arises that tan alpha is equal to alpha. So at these locations, whenever this equation satisfies is satisfied by alpha, we get our maximum positions. So for this, I will, let's say function y is a function y is equal to alpha as well, and y is equal to tangent alpha, because tangent alpha satisfies the alpha. So y, I put a thing variable y which is equal to alpha as well, which is equal to tangent alpha. So I will draw both the equation, both the lines, that y, this is y is equal to alpha line, and these are the value of y is equal to tangent alpha. Okay, now this is a y with respect to alpha. So tangent alpha, these are the tangent alpha graphs, and this is the graph of y is equal to alpha line. Whenever they cross to each other, we will get a maxima. Here I am getting the maxima, here I am getting the maxima, here I am getting the maxima. Okay, so whenever they crosses each other, we will get the maxima. So for minima, now this is the condition for minima, and this is the condition for maxima. Okay, so to find out the widths of the principal maxima or the central maxima, I can find out the condition of the central maxima. We already got that sine theta is equal to sine theta was equal to a sine theta was equal to n lambda. For central, this is sine theta is equal to, now this is the condition for minima. For first minima in this side and for first minima in this side, this should be equal to n is equal to 1, n is equal to 1, right? N is equal to minus 1, n is equal to 1. So this is theta angle, and this is total length x. Okay, so sine theta is equal to lambda by a is the condition satisfied. Okay, or we can also find out using this convex lens focal length. Okay, now this way, here we are using convex lens here at the, now this point is the converging point of this lens. This point, I use this convex lens in such a way that light will all the light coming at this and coming at this convex lens are converging at the focal point of this convex lens. So using that convex lens equation, I can also find out the central maxima. Okay, so this is all done and dusted with our Fraunhofer diffraction due to single slit. Hope you understood it. So try to do it on your own. Thanks.